Hello and welcome to this little session on load stepping in Optum G2. What I mean by load stepping is several things, the simplest case of which is possibly the generation of a load displacement curve for let's say a foundation. So let's draw a box of soil and let's draw some sort of foundation on top here, and let's say that is a Tresca material, that is a rigid material. We have standard fixities, and then we have some load on top here, and we would like to generate the load displacement curve for this foundation. The simplest way of doing that is to apply a multiplier distributed load and then run a multiplier elastoplastic analysis. So multiplier elastoplastic analysis is, you could say, a combination of limit analysis and elastoplastic analysis. Elastoplastic analysis in the sense that a sequence of elastoplastic steps are processed, and limit analysis in the sense that you take that to the ultimate limit. All the usual element types, upper, lower, and 6 node, 15 nodes, and the others are all available. So you can actually do sort of lower bound load displacement analysis to failure in this way. Now, the load stepping itself is described in the examples manual. I think it's example 20. That's 29. It's an introductory example to that. So it's very similar to what I've just sketched on the screen. And then there are some settings. We see here there is this NE elastic steps, NP plastic steps, and then beta step control. What that basically refers to, a typical load displacement curve is sort of an approximately, you could say, a smoothed linear elastic perfectly plastic curve, and what the number of elastic steps refers to is the number of steps you would like up to when things start to become sort of fairly plastic, and then the number of plastic steps is the remaining number of steps until you come out here to something resembling failure. And beta, this value here, the default value is 5, is a sort of a step size control parameter. The higher the beta is, the more aggressive, you could say, the time stepping is, and the lower it is, the more conservative it is. I'll give you full examples here. So let's start with 5 and then let's run an analysis. And you see in the I've taken 10 elastic and 10 plastic steps. So you see in the analysis window here, this of course is not capable really of plotting any displacement, because what displacement would that be? But it's capable of plotting the external work, so the force up here times the displacement versus the load multiplier. So that gives you a sort of a nice looking load displacement type curve. And we see it moves something like that. That's not too surprising. Now, if you want the actual load displacement curve, you would insert a result point up here, and then let's do that and rerun. And we can then go into XY plots and then plot. Well, UI is going to look a little bit awkward, but we could plot the U, sort of the numerical U, the total displacement. So that looks something like this. And this curve here, by the way, you can access the data. Usually you will not be happy with the way this looks, although there is some possibility for customizing the line thickness, markers. All right, I mean, you can customize it fairly well. The text here on the labels and the font sizes and everything else. But If you're still not happy, then you can access the data simply by selecting the curve and then going in here, and then it's copy paste, and then you go into well, Excel, for example, and you can paste it here. And here we go. Here is the data then. Good. So that's the simplest way of generating load displacement curves. And just about this step control, let's try a couple of, let's take one with 2 and one with 10. And let's see how that looks. So the one with 2 is sort of a slightly more careful. And it won't necessarily come all the way to failure either. Whereas the one with 10 is more aggressive. It pushes on in a more aggressive way, and will, in this case, since beta equals 5 leads to failure, then 10 definitely is gonna be failure as well, and maybe we'll even be too far out on the load displacement curve. We're not really very interested in these additional steps here, right? So, but if we plot the 3, first the one with 5, the default value, that looks actually pretty perfect. Then 2, not fantastic, and 10, not really fantastic either. So the default parameters in this case turned out to be the right ones, but that's not a given for any case. So you might need to adjust this beta, this step size control parameter a little bit, or you can do one of a number of other things. So there is the possibility to do what is, there are various other possibilities here. Let's just clone this initial stage here and then have a look at what other possibilities we have in the load stepping. We have the scheme auto. That's basically what I've been running now, right? It's sort of that it runs in an automatic way, and what you get is what you get. And most of the time you get something that looks reasonable, but there's also times when you get something that you wish would be a little bit better. Target allows you to do something about that. So this target scheme allows you to go to a target displacement in the course of a number of predefined steps. And what displacement are we talking about? We are talking about the displacement at the first result point. So if you have several result points, it's the first result point we're talking about, and we can actually override that. So we can say, is this a control point, yes or no? Yeah, I had actually forgot about that. So if we want to do it with respect to the point down here, so this is a result point by default, the first one. The second one says yes as well. That should actually be no. But anyway, if you have one result point, that's is the point that it's the displacements at that point that this target displacement refers to. And if we look at what we had before, we had a displacement, it's the absolute displacement here, up here at this point of 0.03. And we did that, this was in 20 steps, right? 10 elastic and 10 plastic. So let's now try to do the same in 10 steps, 0.03. So this is sort of rather more convenient often than, but you have to have some idea of what displacement, of course, you want to take your system to. But let's just plot the first one, the auto again, with 20 load steps, and then this one with a target load step and with a target displacement, but only 10 steps. And of course, this one is a little more crude, a little more coarse than the one with 20 steps. You can change that to 20, and then you will have pretty much the same. So so those are two ways of doing load displacement analysis, or load displacement analysis. Then there is another way, and we've changed things recently, and that's sort of basically why I'm producing this little video here, because if we look at the final load up here, what did we end up with? Let's say the results are not available. Okay, we ended up with about 185 kPa, so a multiplier of 185, and with for a unit multiplier load. And so if we change this instead to a fixed load and then went to something like, say, 100 and just go 100 and let's go 180, we could in principle run this as an elastoplastic analysis. So an elastoplastic analysis is an analysis where the load is not exactly incremented, the load is fixed. So we could apply this load of 180 kPa in one load step, and we can see how that goes. And we have a displacement up here of whatever, something a little less than what we had before. Of course, the load displacement curve is almost horizontal up at that level of loading. What we used to have up here under settings was the number of load steps, and now it's been moved to advanced settings because it's actually a setting that in the vast majority of cases is best left at 1. It is really not recommended to do load stepping with elastoplastic analysis. Not that you can't do it, but there's just no real point in doing it. It's more efficient to and much more convenient as well to use the multiplier elastoplastic, either with the auto or with the target option that I've just gone through. But we could in principle change that to 10, and the load would then be incremented by in steps of 18 kPa from up to 180 kPa. And that, of course, the result is going to be slightly different between whether you have a single load step or you have 10, right? Because there's some path dependence. So, but it's a very slight difference. We can plot the displacements. Let's try to do that. The vertical displacement, and let's plot the vertical displacement for a single step. And let's then we would need to, of course, have equal scales. I'm not going to do that, but there's a slight difference in these two cases, as expected. Now, but what are you going to do with 10 load steps? What are you going to plot? Well, you could plot the on the x-axis you can plot the displacement, and then on the other axis you could plot the load increments, or maybe the external work. Would that work? Yeah, it's not really in terms of plotting, this is not really extremely convenient, right? Maybe the load increments is actually the better one, or maybe it's even better to turn them around, something like that. I don't know, but so not really a fantastic thing to do this. It's of course a great thing to be able to just do an elastoplastic analysis, find the displacements for a given load in a single step. But I would say if you think you need more than a single step, then you are talking sort of multiply elastoplastic type load stepping, and that's what I would very much recommend that you use. Another possibility, and that's actually an elastoplastic analysis, another possibility is to run things with displacement control. And if we get rid of this load here, and then for that we need a structural elements, but I can use a rigid plate, and let me make this plate so that it is one that sort of moves straight down. So I'm going to prevent rotation, and I'm going to of course release the degree of freedom in the y direction. Now what I can do is I can actually impose a displacement here, and that's go down to the 1 here, and that displacement should be let's say minus 0.03. That was the total displacement before, and there was a bit of rotation, so it's not exactly the same before, but we push this one down by 3 centimeters, right? So a displacement of 3 centimeters is prescribed now. And this, in this case, the number of load steps really matters, right? Because this displacement is enforced, this total displacement of 3 centimeters is then enforced in the course of, in this case, 10 load steps. You can of course use one, but it makes sense to use more than one. It's another way of sort of generating load displacement curves. And so what we go in here, again on the x-axis we want the total displacement, which is the same as the downward displacement of course in this case, because we don't have any lateral displacement. And then on the other axis we can plot the that was my bad. We need actually a result point over here at the reaction in order to pick up the reactions, the forces at that reaction. So I'm going to do that, and then we want and here we want so it's okay, my bad, stage 7 and 0.2 reaction. We want the reactions, yes, thank you. And let's just have the full reaction. Yeah, I think the Y reaction, which is the one we are interested in, yeah, it's going to be negative. So just due to the sign conventions, but we can plot the sort of the total reaction, and that's the one shown here. There will be, I guess, a small X reaction. That's very small. It's very small. So this is pretty much the Y reaction. I mean, that X reaction is of course only due to the fact that the mesh is not completely symmetric, and it's very small. So that's another way of generating load displacement curves by displacement control. But the multiplier elastoplastic is yeah, well, both work. I mean, you can have, of course, cases where a load control is more appropriate, and where displacement control is more appropriate. It sort of depends, but you can do both. Now, just very the final thing I just wanted to say is that I see a lot of times that people do staged excavation type or stage construction type problems. So for example, something like this, and with a let's make it over here with a sort of a sheet pile, and then excavate. You shouldn't. Oh no, of course this, you determine the initial stresses first, and then a new stage where you would which would be an elastoplastic stage, and where you would then excavate. And I'm going to excavate a huge amount of material. Let's try something like that. And for that, I think I'll have to put in, I'm pretty sure I'll have to put in a fixed end anchor. So starting from this, the initial stresses, and then I remove this material and insert an anchor at the same time. And the question is then, what should the number of load steps be for this operation? And the answer is that the number of load steps should be 1. There's really nothing gained from increasing this number of load steps to anything above 1. If you think that the change from one stage to the next is too extreme, which you could argue it definitely is in this case, well then you should have a more gradual transition of the geometry. You should remove this, do the excavation in the course of a larger number of steps than just a single one. But using load steps greater than 1 is not really a particularly good idea. What it just means is that when you transition from this situation to this situation, so you have this and then you remove a huge amount of material and you insert an anchor here. But by removing this material, you of course have some residual forces. So you can imagine you have some forces that are of a certain magnitude in order to keep this sort of initially stable. And then you decrease these forces to zero, and that's basically what the load stepping does. It decreases these residual forces that are in place to make this situation equivalent to this situation. And so these residual forces are decreased in the course of a number of load steps. But that's not really a very physical thing to do, of course. I mean, it's a completely fictitious thing to do. An excavation is removal of material. It's not somehow a gradual and uniform reduction of the residual forces that we have here to start with when we have just transitioned from one stage to the next. So it's a waste of time to use more than one load step, and the result that you get out at the end of the day is, in all likelihood, it's going to be a bit different from what you get with a single load step, but it's not necessarily going to be more correct. The only way to really ensure the correctness of these types of stage construction is to have a more gradual transition of the geometry between the stages. So, but let's just see, for the sake of just, I'm kind of getting curious now, what would it mean to use instead of a single load step, 10 load steps here? You see, you have some weird, you can have some weird effects as well, with some difficulties to convergence difficulties to start with. It's because this is a nonlinear problem, and just sort of shrinking these residual forces is not necessarily really a great thing to do. Let's look at the displacements. That's how it looks for 10 steps, and that's how it looks for a single step. So we are at, let me just try to blow that up by the same. Yeah, so the 10 step here, there's a difference. It's quite a significant difference. Well, actually, no, it seems there's not a huge significant difference. So why do they look so different if they're almost the same? That's weird. So this is 0.0039, and I've scaled it to 100 here, and 0.01, and it's scaled to 100 as well. Okay. I think, yeah, of course, it's the total displacements we should plot. So this is a single load step, 1, 10, 1, 1, 10. So almost the same, and both of them being somewhat questionable due to a far too extreme transition from this initial stage to the final stage here. Load steps is not going to help you. It's just a waste of time, and it's even physically, I think, dubious. So that's pretty much it. I think I've covered the different ways of doing load stepping: multiply, elastoplastic, auto, or target. Then elastoplastic analysis, use a single step, or you can of course use displacement control. That's a possibility as well. And then when it comes to stage construction, stay away from anything greater than 1 in terms of load steps. So that's it, and I'll see you next time.